We now look at a problem known as traversals. Traversals have to do with following paths and accomplishing certain goals with them. So to start this discussion, we will consider a problem known as the bridges of Königsberg. This is a very old math problem that was around in the time of Euler. So in Königsberg, they have a river, which is the path that you sort of see here, and they have some islands and bridges, the red bridges. And the puzzle that legend has is that the claim is that legend says that they used to have a parlor game where they would try to figure out a way to cross all the bridges without repeating any. So why don't we give that a try? So let's start on, let's say, the lower bank here. Maybe I cross that bridge, go across, come back. I'm doing pretty good. But I have a problem. I missed this bridge. So that didn't work. Let's try again. Maybe if I start on an island, I can make it work better. Okay, now I ran into a problem again. I can either go on the top or bottom bridge, but I can't do them both. So you could keep on trying if you want, but I guarantee that unless you do some sort of cheat, like swim across the river, that you won't be able to make this work. So why is that the case? Well, we're going to rewrite this problem in terms of graphs. So this graph here represents the same problem. The way that I've done it is that each island or landmass has been converted into a point. And then if there is a bridge connecting 2 points, we put an edge. So that figure that you see right now, let's see what happens when we go across to there. That's the same picture. So this graph is related to figuring out whether there's a way to cross all the bridges. So since this problem originated in the time of Euler, we have named this problem after Euler. So the Euler path problem asks, is there a path which uses every edge exactly once? That's the same on this question as saying, can I cross every bridge exactly once without repeating any? Now, sometimes we get lucky, and not only can you cross all the bridges or all the edges, but you can come right back to where you started. And in that case, we call it an Euler circuit. So let's give this problem a try in the graph version, and it might help us figure out what's going wrong. A lot of times when you rewrite a problem in a simpler way, it's helpful. Okay, so let me pick a starting point. I'll start on the right. I go up here, down, maybe down again, up. Okay, I have a problem here. I've gone through that center point 3 times. The next time is going to make a 4th when I leave it. And I only have 2 ways I can go, up or to the right. So that 4th time that I touch on that dot, I run into trouble. So maybe I go to the right. And then I can finish down here. So pretty good, but I missed this edge here, that bridge. So I could try this again, but you might notice a pattern at some point. So we had our starting point. Let's see, where did we start? We started right here, and we had our ending point down here. Notice that that starting point has 3 green lines. It had 1 when I left and 2 when I passed through it. So the start has an odd number of edges used. And then if we look at the end point at the bottom, same story. Again, there were 3. There were 2 when I passed through it the first time, and then there was the 1 when I ended. The same thing. What about the other dots? Let's say the one at the top. I came in and I went out. That was even. Down here, I went through it twice, but each time I passed through, I had 1 in and 1 out. So that made even again. So all others use an even number of edges. And so this seems to suggest a pattern. If I can make an Euler path that goes through everything, then it must use an odd number of edges at the start and finish, and an even number of edges everywhere else. If I want the Euler circuit, well, let's see. If I had an Euler circuit, what would change is that last edge would go away. And so the start and end point are the same. And I used an even number of edges there as well. So Euler graph or Euler circuit needs to be even everywhere. Well, it turns out there's a theorem. Euler's theorem says you have an Eulerian path if and only if your graph is connected, which means you can get everywhere, and it has either 0 or 2 odd degrees. Now, those odd degree cases can be broken up. If there are 2 odd degrees, then the Euler path must start at one and end at the other. And that was the pattern we saw here. When we ended down below, we had to start at one blue dot, and we had to end at the other one. The other case, if there were 0 odd degrees, then we have an Euler circuit. So 2 means Euler path, 0 means Euler circuit. So let's look at a couple of these to wrap it up. So look at the graph on the left here. Well, let's ask, does this have an Euler path or an Euler circuit? Well, everything has even degree. So all even, and so it has an Euler circuit. And recall, Euler circuit is also called an Eulerian graph. Now let's look at the second case. We have a funny drawing of a happy face. And the theorem told us, look at the number of odd degrees. So let's see, odd degrees. That one's odd. Here's another one. We have 2. Let's see, 3 and 4. 4 odd degrees. That is not 0, not 2. And so we know that it must not have an Euler path or Euler circuit. So no Euler path, no Euler circuit. On the last figure, all I've changed is that I drew some bushy eyebrows. So what happens now? Looking around, we still have an odd degree down there. And 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. Looks like they're almost all degree 4, except this one right here. So 2 odd degrees. So that means it has an Euler path. And if I want to find that Euler path, I should start at one and end at the other. Now that we know that there is an Euler path, it's time to work on it. I've labeled the vertices because after we find a path, we're going to go back and try to describe it. So let's start at one of the odd degree vertices. I'll start at the nose and see what happens. Well, I've managed to end at the other odd degree vertex, but I was stuck. There's no way for me to fix this. So this does not mean there's no Euler path. It just means my first attempt failed. So let's clear that out and try again. This time, I reached the expected endpoint, and every edge was used exactly once. Now, let's suppose that I need to describe such a path. Well, this was sketched out very quickly, so it might not be reasonable to keep track of everywhere I went, but we can still give it a try. So let's start at H, and then I went to G, D, E, maybe F, and there's many options here. Perhaps I squiggle back to A. Well, from A, I could go back to F on the other part, one with the eyebrows, one at the top of the head. Then we could go back around to A through the bottom, and then over to B. And let's see, what have we got so far? Have we done everything or are we missing some? So H to G to D to E, F, A, back again, around to B. So we're making good progress, but it looks like we have a few more places to get to. So perhaps let's go over the eyebrow to C. And then continue on to D and down around to E again. Around the bottom of the mouth and end where we want to be. So there may be more than one route that works, but the important part is that you can see that we visited every edge exactly once.